We will hear hot topics. And it's my great pleasure to introduce Professor Hugh Thomas. He will speak on flow polytopes and gentle algebras.
Right. Well, thank you for the introduction, Javad. Thank you to the organizers of the seminar for the invitation. It's a pleasure to be talking in this seminar series. I'm going to be talking about flow polytopes and gentle algebras. So this is reporting on joint work with a team of people all from my home university, the University of Quebec at Montreal. And so the team is Antoine Abram, Jose Bastidas, Sarah Browner, Benjamin Dequen, Alejandro Morales, Gaye Park, Franco Saliola, and me. And the paper, I'm sorry to say, is not yet on the archive. We hope to have it done by the end of the summer. So this starts off from a question that I think lots of us may have had for ourselves, or may have had asked to us. If a person is just starting to learn about quiver representations, they're very likely to ask the question, so how is this related to other things that people do with directed graphs? And really, by and large, the answer is it isn't connected to what other people do with directed graphs. There's all these people in graph theory who work on graphs, who have, there's a huge body of literature on graphs, and the quiver representations just doesn't engage with that by and large, which seems, intellectually a little bit unsatisfactory. Like, gosh, we're also thinking about directed graphs. Don't we have anything to say to each other? And so it turns out that there is at least one place where there is something to be said. And so this connects the representation theory of gentle algebras and the combinatorics on flows in directed graphs. And so I'll explain a little bit about both of those topics. So if they're not familiar, I will be talking about them. So this connection between these two topics was first made by a group that I'm referring to just by the initials of their university, because it's a group of people from the University of Kentucky. And so the team consists of Von Bell, Brown, Brugge, Hanley, Peterson, Sarienko, and Yip. And their paper is available on the archive. And so they make a connection, this kind of connection that I'm talking about. And the work that I'm going to be, and so in fact, I'm going to spend a lot of the talk building up to and then talking about their results. And then at the end, I will say something about what we added onto that in our work this year. And I also want to mention that Jonah Berggren, who is currently a graduate student at the University of Kentucky, has some results as well in the same area, making the same connection, but which have a slightly different flavor from our results, but in some respects are even more general. So he has some very nice results. So if this topic is interesting, then you should definitely keep an eye out for his papers. So we're going to begin by talking about flows in graphs. And so I realize this is an algebra seminar, and here I am with a topic that is entirely combinatorial, so this probably won't be familiar. Please do raise your hand if you have a question, or if there's for any reason you want to ask anything. Please do feel free to do that. I'm going to try to explain flows in graphs just quickly. So we have a directed graph consisting of set V of vertices and set E of edges. And our graph is always, the vertices of our graph are going to be divided into three types. V plus, which is a set of sources, V minus, which is a set of sinks. So all the R's are leaving the vertices from V plus, all the R's are going into, all the R's touching a vertex in V minus are going into it, and V0 are the remaining vertices. And we call those the internal vertices. They're not at either end. And the flows in a graph, by definition, a flow consists of a map from the edges to the real numbers, and we're thinking of it as like a quantity of liquid, let's say, actually flowing along the edges. And then the condition that we want to impose that does something to these functions is at the internal vertices, we want so at an internal vertex V, we want to take the sum over all the edges going into V of the flow along that edge, and it should equal the sum over all the edges leaving V of the flow along that edge. So what this is saying is that if we think of it as an amount of flow flowing along the edges, at the internal nodes, the amount coming into the node should equal the amount leaving the node. Okay. So here's an example, a little graph, 8 vertices, A, B, C, D, E, F, G, H. The sources are over here. The sinks are over here. And then we have 2 internal nodes. And then for each edge, I've just given it a non-negative. So by definition, we want the flow quantities to be non-negative real values, but often it's good enough to think about integer values. So I put these integers on the edges indicating the flow. And the thing that makes it a flow is that at the internal vertices D and E, the amount flowing into D is equal to the amount flowing out of D. And the amount, so that's 1 plus 3 is 4, is equal to 4 plus 0. So that's what makes it a flow at D. And then there's also a condition at E that 2 plus 1 equals 1 plus 2. Right? So these are the flows. So combinatorialists are interested in understanding the collection of all the flows. So what kinds of technique could we use to study the collection of all the flows? Well, so if we have a graph G and the flows, as I defined them on the previous slide, this is a convex cone. That is to say, if we have 2 flows and we take a non-negative linear combination of them, it will also be a flow. Now, the reason it has to be non-negative is that we insist that we're flowing water or something along these pipes. We don't want a negative flow. So where the flow is not allowed, we're not allowing negative numbers and flowing backwards and all that stuff. That's not part of the story. So we want to take non-negative linear combinations, and that will still be a flow. And it turns out, because I didn't actually say this explicitly, but it was written down on the slide, that because G is a finite graph, it turns out there's a finite number of flows such that any flow can be written as a non-negative linear combination of those flows. And so expressing a flow in terms of those generators is called decomposing the flow. So it turns out that for this smaller graph, which is actually going to be our example graph, like throughout the talk, where we just have these 5 vertices, you can see that each of these guys is a flow and it has inflow 1 at vertex C and it has outflow 1 at vertex C. So each of these guys is a flow. And it turns out that any flow can be written as a non-negative linear combination of these 4 flows. And you can sort of convince yourself of that, because however much we have flowing from B into C, well, it sort of flows on to either D or E. And so we can use some of this and some of this to account for that. And similarly, for what's flowing out of A, we can account for that using these guys. But the interesting thing to notice here is that there's something a little bit non-trivial going on, because there's different ways of expressing a flow in terms of these 4 flows, because the sum of these 2 flows is equal to the sum of those 2 flows. So there's some linear dependencies, and so there's not a unique way to express a flow as a non-negative linear combination of these flows.
I have a question.
Yes.
For the vertices in V0, do we assume that the number of incoming arrows should be equal to the number of the outcoming arrows? For instance,
we don't assume that in general. I mean, so all we're really assuming is that the sum of the of the flow on the incoming edges should be equal to the sum of the flow on the outgoing edges. We are going to so what is going to happen in the end is representation theory is going to tell us about flows in some directed graphs, and we're going to have to make some assumptions on the graphs involved. And one of those assumptions is in fact going to be that at the internal nodes, there's two incoming vertices and there's two incoming edges and two outgoing edges. So we're going to make that assumption later, but just in terms of the combinatorics, we don't have to make any assumption at all.
Thank you.
Okay, great. So yeah, so we can more generally, we can think about how to write any flow as how to decompose any flow into as a non-negative linear combination of some kind of simpler flows. And it turns out that for sort of the same reason as we saw in the previous example, it's always good enough to think about just taking what are called the routes, where a route is just a walk that starts at a source, goes all the way over to a sink, and just puts a flow of 1 on each of the edges, and that's going to be an actual flow because it just, when it comes to a vertex, it has flow 1 going in and has flow 1 going out. So such a route does define a flow, and then it turns out that any flow can be written as a non-negative linear combination of the routes, basically for the same reason as what I said in the example we were looking at before. And in fact, we can assume more. We could assume that the walks don't repeat vertices, because basically it's not useful to, in a walk, it's not really very useful to kind of go around a loop. You can just remove the loop. Okay, no, sorry, that's not a convincing thing to say. Let me not try to explain why you don't need them, but it's clear that you must have any walk that doesn't repeat vertices, because such a walk clearly can't be decomposed further. And I guess the other point is that if you return to a vertex, then you could decompose that walk into a shorter oriented walk plus a closed walk. So that's the right thing to say about why you can always use only the ones that don't repeat vertices. Okay, so we've now said something about walks. Let me also say something about cones, because the point is that these flows can be described as a cone. We already saw that. And then the question is, how can we better understand, or what is there to say when we've said, well, it's a cone, it's a convex polyhedral cone? What more should we say? What more could we say about it? So let me briefly say a little bit about cones. So if you have a d-dimensional convex polyhedral cone, it certainly needs at least d rays to generate it, right? If you had fewer than d rays is not enough to generate something d-dimensional. If there were fewer, then necessarily that would generate something at most of a smaller dimension. And so in dimensions 1 and 2, for example, any d-dimensional cone is generated by exactly d rays. So here we're thinking of this little picture as a collection of actually cones, 5 two-dimensional cones that are colored in, and then 5 one-dimensional cones separating them. And each of the one-dimensional cones is generated by 1 ray, and each of the two-dimensional cones, so this red two-dimensional cone, for example, is generated by this ray and that ray. And so we see, that for two-dimensional cones and one-dimensional cones, we always have this same number of generators as d, and such cones are called simplicial. Okay, but if d is greater than or equal to 3, then you can have a d-dimensional cone that needs more than d many rays to generate it. And this is basically saying that cones can get complicated. And so here's a little example in 3D of a cone whose cross section is a square. So this is intended to be a cross section of this cone with these 4 rays coming up from the origin and then sliced by a hyperplane. In this cross section, we see a square. And obviously, we could also have seen a pentagon or a hexagon or an octagon, or any n-gon, and that's the whole story in 3 dimensions. But in higher dimensions, it can get even more complicated. But I mean, my pictures are going to not get bigger than 3-dimensional. So this is kind of a typical, well, a prototypical example of a non-simplicial cone. One of the things we can try to do to understand a non-simplicial cone is to decompose it into simplicial cones without introducing new rays. And this is called triangulating it. So in this case, we could introduce we could subdivide by introducing a new 2-dimensional face here that cuts the cone into the part on the left of it and the part on the right. And each of these guys is generated by 3 rays, which is the dimension of these cones. So these 2 guys are simplicial cones, and we've successfully decomposed this non-simplicial cone into a pair of simplicial cones. Okay. Let me just mention for people who might have seen this kind of thing before, you can also, because in this setting there is an ambient Zn lattice in the picture. There's a natural integer lattice in the picture. We could ask that the subdivision be unimodular, which means that when you take any one of the simplicial cones in the subdivision, if you take the first lattice point along each of the rays, that should form a basis for the ambient lattice. So that's asking a little bit more than that it just be simplicial. In fact, what we're going to be doing is going to produce unimodular subdivisions, but I'm not really going to talk about that, but it is true. One reason, just to throw that out there, one reason to be interested in that is that associated to any rational convex polyhedral cone, there's a toric variety, and then a unimodular subdivision is a resolution of that affine toric variety. So there is a link from this story towards actually algebraic geometry. I'm not going to, I don't really have anything to say about that. But I had an interesting conversation with Matt Pressland, who suggested that there really should be something to be said about it. But anyway, so far I don't have anything to say about it. Okay, so let's take a look at, well, actually, so what we're going to do is we're going to look at a very simple example and just look at this this graph again, which is going to be really my running example throughout the talk. So I have 5 vertices, and my flow I'm just denoting by F1, F2, F3, and F4 are the amounts of flow on the 4 edges. And the flow condition says that F1 plus F2 equals F3 plus F4. So that means that although the flow cone lives in the 4-dimensional space of the values of the 4 tuples, F1, F2, F3, F4, actually it's living in a 3-dimensional subspace of that. So that means we can actually draw the flow cone. And this is what we get when we draw the flow cone. So here's the graph again. And then these 4 lattice points are marked here, 1, 0, 1, 0, and so forth. So these are these 4 lattice points, and they correspond to the 4 roots that I talked about earlier. So these are 4 lattice points in this cone, and they generate the cone, as we said before. And so that tells us in particular that this really is the picture of the flow cone for this graph. Okay. So that was the crash course in flows in networks. Are there questions about that? Okay, well, super. So I'm just going to carry on with a quick reminder on gentle algebras. So I'm going to try to do a quick intro to gentle algebras for those who haven't seen gentle algebras before, It may be a little bit too fast, but the idea is that they're a kind of, so they're quivers with relations that have some special kind of conditions and that have some particularly nice properties, and we can understand their representation theory particularly well. So the setting really is in quivers with quadratic zero relations. So a quiver with a quadratic zero relation is just a quiver and a collection of pairs of arrows, composable arrows, so that alpha 2 immediately follows alpha 1. And then a representation of such a pair is just a representation of the quiver such that the composition of the corresponding maps, of the maps corresponding to the relation, is 0. So this is kind of the easiest sort of quiver with relation. And so normally when we draw a picture, we just draw it, we put a dotted line like this to indicate that there's a relation that the composition alpha beta is supposed to be 0. And so, for example, for this quiver with 3 vertices, 2 arrows, one of the indecomposable representations of this quiver is not an indecomposable representation if we put this relation on there, namely the representation that just puts a copy of the ground field at each vertex and identity maps between them. That guy is not a representation of this quiver with relation because that composition is non-zero, but all the other indecomposable representations are because the composition is 0. Right, so that's what it means to be a quiver with quadratic relations. And so locally gentle quivers with relations satisfy like some weird combinatorial conditions, which I'm going to explain quickly, but then we're going to look at a picture which is more illuminating. So the in degree is at most 2 at each vertex. The out degree is at most 2 at each vertex. For every arrow, there is at most 1 arrow that carries on from it, which forms a relation with the first one, and there's at most 1 that doesn't form a relation. And also, for every arrow, also for every alpha, there's at most 1 gamma, so that gamma alpha is a relation, and there's at most 1 so that gamma alpha is not a relation. So, that takes a little bit of getting used to, but what it means roughly is that around any vertex V, the quiver looks like this. There's at most 2 arrows coming in, there's at most 2 arrows going out, there's a relation here and a relation here, and then it turns out we can take this picture and we can remove some vertices if we like, we can identify some vertices if we like, but basically what it means is that locally the picture looks like this. And so that was locally gentle. It's gentle if also there are no oriented cycles. No, sorry, that's not. Yeah, so no oriented cycles with no relation. Sorry, that's the key point is that what's not allowed is oriented cycles with no relation along the cycle. So a quiver with relation can be thought of as defining a quotient of the path algebra generated by relations. For a locally gentle quiver, QR is gentle if and only if the quotient is finite dimensional. So locally gentle algebras, not necessarily finite dimensional. Gentle algebras, finite dimensional. And so we like finite dimensional things better, but it turns out that a bunch of the theory also works in the locally gentle case, and that will turn out to be relevant for us. So this is probably the most technical slide of my talk. It's not so important to really fully grasp what's going on here. The point, though, is that there's a certain kind of, so the point of this slide is just that I'm defining a certain kind of walk in the quiver, and then what we're going to do is we're going to use that. So to each string walk, I'm going to, well, I'm not really going to define it, but to each string walk, there is an indecomposable representation that corresponds to it. So string walk is specifically, it's a walk in the quiver. We assume the quiver is locally gentle. Each step in the walk is allowed to go either with or against the direction of the arrows, which might not be the most intuitive thing, like at first glance. So the walk is allowed to go with or against the direction of the arrows. So it's a sequence of vertices and arrows alternating vertex, arrow, and so forth. But we record these signs, SI, that's to keep track of whether we're going with the arrow, which is SI equals 1, or against the arrow if SI is -1. And then there's a few conditions. You're not allowed to immediately backtrack. So if you take an edge, you're not allowed to then immediately take the same edge in the opposite direction. And you have to avoid relations. Whenever it would make sense for there to be a relation, it's not allowed for it to be a relation. Okay, so that's a certain class of walks in a quiver. And then the point is that to each string walk, there is an indecomposable representation, which is called a string representation. So these were originally introduced by Butler and Ringel. And to define the representation, you just kind of proceed along the walk. You think of it as a walk. And you put down a copy of the ground field at each vertex as you walk along. And then the arrows between successive copies of the ground field are just non-zero maps. And so that fully defines the thing if you don't revisit any vertex more than once. If you do revisit a vertex more than once, you'll have put down multiple copies of K at that vertex that you revisited. And because you put down a copy of K each time you visit it. And the point is that you just, the different copies of K that you're putting down just don't interact with each other. It's just as if they were, so they just don't interact with each other. Anyway, so the point is we get this beautiful class of indecomposable representations for our algebra. And it turns out that for a slightly more special class of quivers, this will be all the indecomposable representations. So in general, in Butler and Ringel's work, there's a second class of representations called bands, which also show up. But for the case that we'll be most interested in, that will not happen, or practically not happen. That will practically not happen. So now we've had our introduction to flows, and we've had our introduction to gentle algebras, and now I want to talk to you about sort of getting to the point. I want to talk about triangulating the flow cone. And so this work that I'm presenting now is the work by the group from the University of Kentucky that we were building on. So I want to begin with sort of a teaser. We saw that if we wanted to understand the flow cone here, we needed to think about the 4 roots in this graph, right? So these were the things going A to C to D, A to C to E, B to C to D, B to C to E, right? So that was what we wanted to understand. Now, in this quiver, now this I'm going to call a quiver because, so this is the graph that we're doing flows in. This is a quiver that we're doing representation theory in. And what we notice is that here, there are strings that exactly correspond to the roots. And in order for that to be true, though, we had to change some orientation. So it wouldn't have worked just to take the flow graph and to try to represent that graph. That's not quite the right thing to do. We have to change the graph in a certain way and introduce some relations on it. But once we do that, the strings, the roots here correspond to strings over on this side. Not just all the strings though, because a string can be short. So yeah, so let's so how can we take that teaser and turn that into some kind of more general idea? Well, so we're going to assume that G is an oriented graph with the tripartition of the vertices, like we already saw. Also, we're going to assume that the edges of G are 2-colored, so that every edge of G is either red or blue. And we're going to assume further that every internal vertex has 1 arrow of each color entering it and 1 arrow of each color leaving it. So, it's quite a special configuration. The sources and sinks we're going to assume are degree 1 just for convenience. And then the setting of the graphs that we're interested in are these bicolored graphs. And the folks in the University of Kentucky assume that these are bicolored graphs with no oriented cycles. So now we want to go from the graph to a quiver with relations. So what we're going to do as first step to get the quiver, we're going to reverse the red arrows. And I underline the R's just to as a kind of mnemonic. So the blue arrows are going to stay the same, but the red arrows are going to be reversed, and that's going to give us a quiver. Then we're going to impose relations, and the relations are a red arrow followed by a blue arrow is a relation, and a blue arrow followed by a red arrow is a relation. So under those assumptions, and we'll look at an example in just a sec, but under those assumptions that we talked about, G is bicolored and has no oriented cycles, we get from this a gentle quiver with relations. Also, all the indecomposable representations are string representations. So we really have a classification of the indecomposable representations by strings. And it turns out that these indecomposable representations are also what is called tau rigid, which means that hom x tau x is 0. And so this is going to be important. If you've heard about this stuff before, this is something that comes out of the set of ideas called tau tilting theory, and we're going to see that tau tilting theory is going to be very important. And if tau tilting theory is something you've heard of before, you can start to think about how could tau tilting theory possibly be relevant to what we're talking about. So just to see again what happened here, we started with a quiver, which was bicolored, the condition. So these guys are sources, they're degree 1, sinks, they're degree 1. The internal vertex here has 1 incoming red edge, 1 leaving red edge, 1 incoming blue edge, 1 leaving blue edge. So great, that makes it a bicolored graph. It also has no oriented cycles. So right, so there we are. That's the Kentucky setting. They use a slightly different language to talk about it, but this is equivalent to their setting. And now to get a quiver, we're just reversing the red arrows and we're introducing a relation that says that blue followed by red is 0 and red followed by blue is 0. So there we are. And so basically the same picture from the teaser shows that the local condition that defines a string walk is equivalent to the local condition that defines a route. I mean, what does a route look like? A route looks like flow comes in, unit flow comes in along one edge, and it leaves along one edge. Right? So here's this. We can think of this now as a local picture inside of some bigger graph. The local condition at C to be a route is, well, there's a unit of flow coming in along one of those edges, and it leaves along one of those edges. The local condition to be a string passing through vertex C is, well, if it comes in here, it can leave on one of those two, or if it comes in here, it can leave along one of those two. So the conditions are exactly the same. And so what that guarantees is that the routes for G correspond to a special kind of string representation for Q with the relations R. So that's already kind of sounding a little interesting, but it isn't quite the algebraic setting that we want. The issue being that there's, not all the string representations are corresponding to roots at this point. So we want to do something slightly different. And so what we're going to do is we're going to throw away the sources and the sinks. And so we're going to define QG tilde to be the quiver QG restricted to V0, and this should be RG tilde to be RG restricted to QG tilde. Okay, so we're taking a smaller set, taking a smaller quiver and looking at the representations there. And then it turns out that folks in the University of Kentucky showed that there's a bijection between the indecomposable representations plus something else that I'll explain in just a moment to the non-monochromatic roots of G. So So while we threw away some monochromatic roots, there aren't, well, relatively speaking, there aren't very many of these monochromatic roots. We're just going to ignore the monochromatic roots. Over on this side, we have the indecomposable representations, and we have what I call the shifted indecomposable projective representations. So these are things that also show up in tau tilting theory, and so they're not actual representations. They're just, we can think of them as just like a formal symbol for each indecomposable projective. We introduce the formal symbol, we write pi shifted by 1 for some thing that we're going to talk about kind of as if it was a representation, but it isn't one. And so we can just work like that. There's more sophisticated ways to talk about this. If you like, you can think about them in a more sophisticated way. You can think about these together as being objects in the homotopy category of projectives, in the two-term complexes in the homotopy category of projectives, if you want. But you don't have to. You can just treat these as sort of like just extra guys, which we just threw in there because otherwise we wouldn't get a bijection. And so I'm not really going to explain this bijection. It's close, well, it's related to the bijection that were the inclusion that we saw on the previous page that said that roots correspond to a certain kind of representation on the bigger quiver. Anyway, and it's related to the Auslander-Wrighton translation, really, is what is kind of at the heart of this. So what's the interest of having these guys, in particular, these shifted indecomposable projective guys? What's the interest of that? Well, there's a thing called the G-vector fan. And so this is really at the heart of tau tilting theory. For any finite dimensional algebra, there's a fan, a collection of cones, and non-overlapping and intersecting in nicely, but I'm not going to get into the details, called the G-vector fan. So the rays are the G-vectors of the tau-rigid indecomposable modules, plus the G-vector of the shifted indecomposable projective modules. So the G-vector of an indecomposable module is just defined by taking a minimal projective presentation. So that there's my minimal projective presentation, and then I just consider the free abelian group on the indecomposable projectives. So that's just it's just a free abelian group whose rank is the number of vertices of my quiver, and the G-vector is just the class of P0 minus the class of P1. And this is like a slightly fancy way of saying it. I mean, what this amounts to is that G is just going to be an n-dimensional, is just going to be a vector in Zn. I just wrote it this way, and I didn't choose a basis. But so basically, just the G-vectors are just vectors in Zn, and then the G-vector of a shifted projective is just by definition negative the class of the corresponding projective. And then there's a certain compatibility relation that says which, how do you decide which rays fit together to make cones? And so modules are compatible if we have this Hom vanishing condition. Module is compatible with shifted projective. Again, there's a vanishing condition, and the shifted projectives are always compatible. So that's a lightning introduction to G-vector fans. Let me just give you a couple of examples just to have something in your mind about what they might look like if you've never seen such a thing before. For the quiver that consists of just a single vertex and no arrows, well, there's one indecomposable, well, so this is supposed to be happening in the free abelian group, or sorry, in K0 of proj lambda, so that's the free abelian group on a single generator. So this is just happening inside of Z. We have an indecomposable that is just the simple indecomposable. It's projective, so its class is just itself. And then we have the shifted projective, whose class is negative itself, and that's it. So that's the G-vector fan. We just have two rays pointing in opposite directions. For this quiver, we have two projective in decomposables with these two rays. We have the simple non-projective, which is this ray, and then we have the two shifted projectives, whose classes are the negatives of the classes of the projective. So the basis is the projective at well, one of A and B, and this is the projective at the other. Okay, so these are some examples of G vector fans, and we have the compatibility that is drawn here. And it turns out that if there's only finitely many rays, then the cones cover the whole space. So it's really it's a complete, what's called a complete fan. So the result, the main result of the Kentucky group was that for G, a bicolored graph with no oriented cycles, as before, there is a combinatorial bijection between the maximal cones and the G vector fan for the quiver, where we've reversed the red arrows and removed the sources and sinks, and the simplices of a certain triangulation of the flow cone. And the way the map works is just we look at the G vectors, we take the corresponding flows, and then we add in the monochromatic flows. Because remember, the monochromatic flows sort of weren't in the picture. We just add them in. We add them into every simplex. And then this gives us, it turns out, the simplices of a triangulation. So this was a known triangulation of the flow cone defined by Danilov, Karzanov, and Koshevoy. So, so this is now, I mean, I think this is a really lovely result. We have, really in a non-trivial way, we have the G vector fan from tau tilting theory talking to this triangulation of the flow cone. And this yeah, so I think that's a really nice result. So now let me, in my remaining few minutes, say a little something about what we did this past year. So it turns out that the combinatorial bijection, so the previous theorem just said, oh, we have the same combinatorics. We had already said that the rays, the roots in the graph corresponded to the rays in the G vector fan. And then their result was that actually was a combinatorial isomorphism between the two fans. Well, it turns out that there's a linear isomorphism. So again, same setting, G, bicolored graph, no oriented cycles. Then there's actually a linear isomorphism. You take the DKK triangulation, and you take the subspace spanned by the rays corresponding to the monochromatic roots. You quotient that out, then what you get is on the nose, the G vector fan of this quiver with relations. And then we know stuff about, and this dictionary can now it can go in both directions. There's stuff that we know about G vector fans. We know G vector fans are unimodular, for example. And so that means that recovers a result from DKK, that their fan is unimodular. So they had to prove that. We just know it from representation theory. And so, but you could also think about this going in the other direction, where you might say, where you could think of this as saying, all the combinatorics that people have spent time thinking about, the combinatorics of these DKK triangulations, and people have spent time thinking about that. They were actually studying G vector fans without knowing it. And so now we know a lot. We have we have a lot of explicit detail worked out of G vector fans. If you were ever saying to yourself, well, this G vector fan stuff, it sounds interesting, but what do examples actually look like? Well, it turns out the graph theorists have a whole bunch of examples for you if you want. So there we are. And so there, right. So let's have an example of this. So here, remember, was the flow cone, and here was a triangulation of the flow cone where we subdivided it into two simplices. These two, so this is the triangulation that comes from the University of Kentucky. These two roots are the monochromatic roots, and so we have two simplices both of which contain all the monochromatic roots. If you quotient out by this plane, well, now this fan, which used to have these 4 arrays, well, these 2 arrays have just gotten squashed down to 0. We don't see them anymore. But now we have 2 rays on opposite sides of this 2-dimensional hyperplane. And so as a result, when we've quotiented out, what we just see are the 2 arrows that are left in a 1-dimensional vector space, because we were 3-dimensional, but we quotiented out by something 2-dimensional. So we're now in 1-dimensional vector space. And the rays are now going in opposite directions because they were on opposite sides of the 2-dimensional plane. And this is indeed the G vector fan, as we said, for the graph, for the quiver that consists of just a single vertex. Yeah. And so the other main thing that we did was to think about what happens if G contains cycles. So if G contains a cycle that can have, like, so and by cycle I mean oriented cycle. So if G contains a non-monochromatic oriented cycle, there will be an infinite number of cones in the G vector fan. And that's sort of a little undesirable from the point of view of the people doing graph theory. They like counting these things. Well, the answer will just be infinity. I mean, it's also very interesting, but anyway, we just sort of looked at that and we said, well, maybe that's for another day. But it turns out that if the only cycles in G are monochromatic, then we can say something very nice. Because of the cycle, the quiver with relations is only locally gentle, but that's not a big problem. It still has a G vector fan by work of Aoki and Yorikusa. And then what we can say is that there is a linear subspace of the G vector fan consisting of G vectors of finite dimensional modules and is triangulated by the restriction of the G vector fan. So we don't want to take exactly the classic G vector fan. We want to take a linear subspace of the G vector fan, but there's a natural linear subspace. There's a DKK on the other side. There's a DKK style triangulation of the flow cone. Now this is outside the setting of DKK, but there is still, there's still a flow cone for sure. And it turns out there's a DKK-like triangulation. So this isn't one that DKK provided. This is one that we provide, but it's of a very similar nature. All the cones contain all the monochromatic roots, and that includes the monochromatic cycles. You include them as well. And we have a result similar to the case where there are no cycles. The quotient of the triangulation from 2, so the quotient of this DKK style triangulation by the span of the rays corresponding monochromatic roots is linearly isomorphic to the linear subspace from here. So we again get the same kind of bijection between the triangulation of the flow cone and a G vector fan. And yeah, so just to summarize, the results from Kentucky say there is a way to triangulate the flow cone of a bicolored oriented graph G, which combinatorially corresponds to the G vector fan of a certain quiver with relations defined from G. And our results were that this correspondence isn't just combinatorics, it's really a linear algebraic isomorphism. And also, you can introduce oriented monochromatic cycles into G, and the same story still works, and you still get the same picture. Okay, so that's what I wanted to tell you. Thank you very much.
Thank you very much for your nice presentation. Yeah, it was very interesting. Are there any questions? Or comments?
So thank you for your very nice talk. I have a question. Is there some connection to the structure of the cluster algebra in one side and some, the graph theory property of this graph? For example, is it possible finds the basis for the cluster algebra, corresponding cluster algebra in a quiver part by using some Volk or in a graph?
Okay, yeah, okay, that's really interesting. So the so these G-vector fans were, of course, developed. I mean, the term G-vector fan comes from cluster algebras. The G-vector fans of tau tilting theory were developed by people who knew about the story for cluster algebras and who were I think, really fascinated to discover that, in fact, G-vector fans aren't just for cluster algebras. You have a perfectly nice, interesting G-vector fan for any finite dimensional algebra. In the case when the cluster algebra is not of finite type, then the G-vector fan has more than has infinitely many cones and doesn't cover the whole space. And so we, in terms of what's gone on so far in this story, that kind of situation has been avoided. In this case where the G-vector, where we haven't really thought about the situation where the flows are where the G-vector fan would have infinitely many cones. So that means that kind of restricts us to the situation of finite type cluster algebras. So the type A cluster algebras, really do fall within this setting. There's a way to describe. So this all works perfectly in that case for any orientation of a type A quiver. You get a you can sort of add in sources and sinks to make this kind of story applicable, and so you get Catalan many maximal cones, which are therefore naturally corresponding to clusters. Now, I think it would be interesting to think about what's going on in other finite types, and to ask, what can we? Is there some notion of flows, some suitable notion of something like a flow that would correspond to the G-vector fan for a type D cluster, cluster algebra, and that's not something that we've done. I don't think anybody has a description like that. I think that would be interesting, and type E as well. Type E is something where there's no really satisfying combinatorial description of the combinatorics of the cluster fan, and so maybe there's some flowy way to think about it, that would be very interesting.
Thank you.
Are there other questions? Can you just remind me what you mean by a DKK triangulation?
Right. Well, so Danilov, Koshevoy, and Karzanov defined a triangulation. So in a purely combinatorial setting, they defined a triangulation of the flow cone. And so the interesting thing is that it turns out that you can recover that using representation theory. And I mean, why is that interesting? Well, and so you get for free some facts about their triangulation. For example, that it's unimodular, because via this dictionary that says that, well, it corresponds to a G-vector fan. We know the G-vector fan is unimodular, so the DKK triangulation was unimodular. Now, I mean, I think if you went to some combinatorialists and said, you can save writing down a page-long proof of unimodularity by going and learning all about tau tilting theory, they might not be fully convinced that that was a good trade, right? Because you have to learn a lot of tau tilting theory to understand that the G-vector fan is unimodular. But it's still kind of, I think for us, it's still appealing that and the other thing that is really interesting, I think is really interesting, is that guided by the by representation theoretic considerations, we were then inspired to define this DKK style triangulation, what I was calling DKK style triangulation, where the graph was allowed to have oriented cycles. That's something that DKK didn't ever consider. I mean, they could have, but they didn't. And so one of the things that's interesting is that the algebra is suggesting things to combinatorialists that they don't, in the end, they don't need the algebra necessarily to think about, but the algebra, has some good ideas about where is there interesting stuff going on. And then so we can come back to, in this case, to come back to the combinatorialist and say, look, there's really interesting, the algebra is telling us that things are really interesting when you introduce these monochromatic cycles. Maybe that's worth studying. And so now one can study that in a purely combinatorial way. And in fact, you can generalize the triangulations that we introduced from representation theory. You can generalize them back in this setting with oriented cycles more generally if you want.
And another naive question, actually using an oriented bicolored graph, after some steps, you reach out to a gentle algebra, okay, to the quiver of a gentle. Is it true that every gentle algebra can be obtained in this way from a bicolored graph?
Well, so we made some assumptions because let's see, so all right, so we made the assumption that the vertices, we made the assumption the internal vertices all have degree 2, but somehow the natural thing to do is to hope, if you have a gentle quiver, it turns out that there's exactly one way that you can add sources and sinks to it to make it be to make it have these properties. So not the bicoloring. The bicoloring is sort of special. So that's kind of an additional condition. But sorry, the issue about like the edges colored red and blue, that's sort of special. In particular, yeah. So there are some special things. I'm sorry, I'm not giving a very coherent answer. I mean, just to address specifically the kind of things that they considered at the University of Kentucky, their gentle algebras have some additional properties that all the indecomposables, that there were finitely many indecomposables, and they're all tau rigid. So that's not true of a general gentle algebra. And even when you introduce these oriented cycles, there's still somehow, yeah, so it's still in some respects special. That said, there is sort of a story that's a bit like what you asked about, which is you can take any general algebra and you can add sources and sinks to get something where the internal nodes have degree 2 and the sources and sinks have degree 1. And anyway, sorry, the reason that I'm advertising that is that it's kind of a key construction. I mean, it's a very simple idea, but it's sort of a key construction in some earlier work that I did with Thomas Brusle and another set of students. And also that was also done at the same time by Pierre-Guy Plamondon, Vincent Pilot, and Yann Palu. And some of those ideas also play into this correspondence here that's turning these inequal representations into roots.
Can you name a few people in the University of Kentucky group?
Yes. Sorry, I did list them at the beginning. Yes, sorry. I mean, and I didn't intend any disrespect in repeatedly not giving them names, but they here they are.
Awesome.
So Kristina Seryenko is the person from representation theory that you might be most likely to know. I know Martha Yip. I've met Matthias von Bell. I'm afraid I don't remember the first names of Brown and Brugge. Hanley. I think Peterson's first name is Zachary, and I've met him as well. He is. I think he was a student of Christina's, and so he is also coming from the representation theory side. That some of these people are really coming from combinatorics, and it's just by I think really just a coincidence that they all they all happen to be in Kentucky, so they just at the same university, so they started talking to each other, and they realized, oh, there's something really interesting here that we should dig into.
Thank you. Are there more questions or comments? If it's not the case, let's thank the speaker once more. Thank you very much.
Well, thank you. It was really a pleasure.
I hope we could have you in Isfahan in person in the near future.
Yes, well, I hope so.
Thank you very much.